the birth of modern physics. A philosopher once said, "It is necessary for the very existence of the science that the same conditions always produce the same results." Well, they do not. Do not keep saying it to yourself. But how can it be like that? Because you will get down the drain, into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that. Richard Feynman, on quantum physics, the character of the physical law. Classical physics developed steadily, starting with Isaac Newton's ideas in the 1600s and progressing through the 1700s, 1800s, 1900s. The ideas of forces, gravity, electricity, magnetism, ideas about temperature, thermal physics, light, and sound. All of this was being developed and understood. I think there was a sort of the sense of the contentment among the physics community members in the late 1800s that we really had established a scientific method and a scientific framework that could describe the world very deeply and very truthfully. But there were some inklings in the late 1800s that there was something deep and more important missing, and today I want to talk about this transition that was made pretty much right around 1900 from what we now call classical physics to what we now call modern physics. Yes. This transition was forced upon us by inconsistency between the theoretical calculations and the data that was observed in the laboratories. The first one, or at least the one I think is perhaps the most influential in the transition from the classical to modern thinking, was understood for the first time, or at least tentatively understood by a fellow named Max Planck. Max Planck was a German physicist who went into the college very young. He was a brilliant young fellow. He went to the college at the age of 16, and an older professor told him, "You shouldn't go into physics because we pretty much know everything. It's a closed and almost dead field. Ha ha ha." Fortunately, Max Planck wasn't paying much attention to this old guy. He started studying all of the classical physics that was known and got very interested in the problem of what happens when the object heat up and start to glow. It just seemed like a ripe topic to put together all of physics. You've got atoms in the material that are jiggling because they are how, and you've got to understand electricity and magnetism. Because after all, when something glows, what is really going on? Is there are little electric charges jiggling around and they emit electromagnetic waves, electromagnetic radiation, which is light, and you need to understand thermodynamics. You really have to put together everything that you know about classical physics. Right. People had been trying to do this for quite some time, and they were discovering a big disaster. You'd do the calculations following the laws of the classical physics and conclude that the color that you would predict was completely wrong. In fact, you get crazy answers. You get an infinite answer for the amount of the energy being emitted by some glowing object at ordinary, fairly high temperatures. So this is a big puzzle. It was some sort of the dilemma for classical physics. Yes. Max Planck studied the problem, and the first thing that he observed was there was no mistakes being made. Classical physics was capable of solving this problem, and you worked out this detail, and you disagreed radically, widely with the data. So, the next thing that Max Planck decided to do was kind of play the role of Kepler. Really? Collecting data? No, assembling the data, right? And yes. Remember, Kepler was looking at the data describing planetary motion, and his idea was not to explain the motion, but just to describe it. That's always a good first step in the science, just to describe the data quantitatively. Yes. So Max Planck sat down and looked at the data and had been taken. The data was a sort of, when something starts to grow, it gets red, and when it gets hotter, it gets bluish and then whitish. This was a phenomenon that he was really trying to describe quantitatively, and he was able to come up with a formula which describes the temperature and the color behavior of hot objects, right? The formula matched the data, so it seemed to be in agreement with what people were observing in the laboratory, but it had no fundamental explanations. It was simply a description, but not an explanation, right? There is a difference between the description and explanation. Thus began what Max Planck calls the most strenuous work of his life. Let me quote from him. The whole procedure was an act of the despair, because a theoretical interpretation had to be found at any price, no matter how high that must be. You've got to realize that this is a very insightful idea in the 1800s, when people are quite satisfied with the nature of physics and science. And this guy is saying, look, we've got an irreconcilable difference. We've got to understand it. So he's banging his head against this problem. I love this. It's this strenuous work, right? Theoretical physics, when you are sitting quietly at your desk thinking it's really strenuous work. Wow. So he did come up with an explanation, and he wasn't completely satisfied with it. But here was his explanation. Let me tell you something first about electromagnetic waves. Yes. When you jiggle a charge, little electric charge makes electromagnetic waves which travel away. Yes. And that's what we call light. Light is a wave. It's a wave like any other wave. Physicists understand waves very well. In the late 1800s, wave mechanics was a very, very well developed branch of the physics. Imagine poking your finger into a pond, you'll create a wave. So your jiggling finger in the pond is like a jiggling electric charge, and water waves will emanate from that, and we understand how waves behave. Yes, good analogy. Waves are very special things. For instance, two waves can pass through one another. While they are passing through one another, they interfere with one another, but then they continue on their merry way. Waves can bend around corners. They have various properties that are very distinctive, and all of those properties have been experimentally verified, have been observed by light rays. Light rays can bend around corners. Light rays can pass through one another. Light rays can interfere with one another. So people really were convinced from the early 1800s on that light is a wave, and there were theoretical arguments that were very, very compelling that this was a fact of nature. Wow. But Max Planck was willing to challenge this the scientific framework of the time and said, what if this is his brilliance? What if atoms, little jiggling charges, do not emit electromagnetic waves, but instead emit light in little pulses, little flashes? So we now call those little chunks of light quanta. So little chunk of the light, quanta of light for individuals, little bundles of the light. Now this is a crazy idea. It doesn't fit in with the theoretical framework of the day. But Max Planck just asked, what if? He worked out the calculations and surely enough his description of this data of hot object matches with this crazy idea. So he has taken our idea about light and turned it on its head. He says, no, it's not a wave after all, it's a little bundle of particles. Wow. When you look at the light bulb, think of a stream of little BBs of the light coming at you. That's the new image of the light that Max Planck is proposing. It's in contradiction with the data from the early 1800s, but in agreement with this new data. Wow! Max Planck got a Nobel Prize for this work in 1918, but he never really believed that. What he was describing was fundamentally a statement about nature. He thought that he had discovered a mathematical solution to the problem, a kind of the formal way of the thinking about light that wasn't really describing the light. Wow. So that was 1900 when Max Planck published that paper. 5 years later, in 1905, there was a young physicist who at that time was barely known. He had his PhD, but he couldn't get a job as a physics professor, so he took a job at the patent office, and he was a smart guy. Yes, this is who he is, right? This was Albert Einstein, and he spent most of his day thinking while he was at the patent office, because the patent office work was pretty easy to him, right? Yes. In 1 year, 1905, Mr. Einstein published 3 papers. These were referred physics papers in the journals, even though he didn't have the position at the academic institution. Any one of those 3 papers was so brilliant and so remarkable that he would be famous today. If he had just written one of them, he would be easily as famous as Max Planck. But he wrote these 3 papers in what is sometimes called his miracle year. These 3 papers were very influential in the transforming our ideas about physics from the classical to the quantum. Right. So let me just briefly summarize. One of them was his paper on the Brownian motion, which I talked about in the last lecture. It was a quantitative understanding of how atoms bumping into small objects, such as little pieces of the yeast or pollen, would make it jiggle around. It was a quantitative demonstration that atoms are real. That was an important and influential paper. Another that he wrote that year was his special theory of relativity, for which he is most famous, E = mc squared, and all that good stuff. I would love to tell you about relativity, but it's a whole course unto itself, so I'm just going to leave this theory of the relativity. You'll have to go to learn about it elsewhere on your own. There are a lot of resources available. Relativity is tough going. It's kind of the counterintuitive, but you can understand relativity without working through very much or even any mathematics. So I would encourage you to learn more. Thank you. Yeah. What I want to say about it is simply that special relativity changed our worldview about space and time. Albert Einstein has explained to us in this paper that time and space are intimately connected. Yes, which is in other words, it's compatible, right? He called it a space-time, and this connected fabric. It's what we live in, is what physics lives in. This space-time, it's not the way we had thought for hundreds of years. It's not universal and independent of observer. So this is Einstein's theory of relativity in super nutshell. Although in principle you need a relativity to understand particle physics, which is this course. In practice we can really understand most of what we need to know about particle physics without invoking any of the details of relativity. What I want to focus on today is Albert Einstein's third paper from that year, which was on the effect called photoelectric effect. Yes, I've studied a lot at the university, at the medical school, right? The photoelectric effect, photoelectric, it comes from light and electricity. It was known in the early 1900s that if you shine the light on a metal, that electricity would come out. Wow. This is extremely well known today, like solar panels. Light comes in, electricity goes out. Also, you take your little remote controller and you click the television set. Infrared light hits some detector on the TV set, electricity comes out, gives a signal. Wow! Photoelectric effect is useful technology today. At that time, it was a big mystery because people thought that the electromagnetic radiation light was a wave. Right. People were picturing a wave, like a wave at the beach, coming up and striking the metal, which is like the beach. So the pebbles on the beach are like the little electrons, and the wave jiggles the pebbles a little bit. That's your mental model in a classical terms of the light hitting metal, and what you would expect classically. You would make a number of predictions based on this worldview. For example, if you have a intense wave like a tsunami, those pebbles are going to go flying because there is going to be lots of energy. You'd expect that electrons coming out from the intense light should have lots of energy, but what you see is completely contradictory data. Wow! It's kind of like Max Planck, who was looking at the data from glowing hot objects that were in the contradiction with the classical ideas. Einstein is looking at the data which is contradictory to the classical physics, and he said, "Let's take Mr. Planck's idea seriously. Let us believe that electromagnetic radiation comes in the form of the little bundles, little cones of the light. So now we are imagining of the kind of the pellet storm hitting those pebbles on the beach, and any one individual pellet of the light can hit one pebble and knock it free. This makes different quantitative prediction, and Einstein worked them all out." That was his paper. Wow. This was a paper for which Einstein won his Nobel Prize, by the way, in the 1921. It's a little bit interesting that Einstein did not get his Nobel Prize for the relativity, not for E equal mc square, not for his understanding of the gravity, not for all the stuff for which he has now most famous. It's an interesting social and political physics story, which I will leave to you to learn more about because it's sort of fun stuff. Professor Stephen Pollock, you are so funny, interesting guy. So Albert Einstein has taken Max Planck seriously. Max Planck didn't take himself seriously in the sense that he didn't really continue working on this idea of the light quanta. But once Einstein weighed it in on the topic, people began to take the idea a little bit more seriously.